This battery looks like one number, 3.1 volts, but that single number is hiding almost everything that is actually wrong inside it. Poke it gently, though, at exactly the right rhythm, and it draws you this. A strange, comma-shaped curve. By the end of this video, you will read this curve like a sentence and tell whether a battery is healthy, freezing, or quietly dying without ever opening it. So let's poke it. You know Ohm's law. Voltage equals current times resistance. One number, but what if the voltage isn't steady? What if it gently wiggles up and down like a sine wave? We add a tiny ripple, just a few millivolts, on top of the battery's resting voltage. So gentle, it is like tapping a wine glass to hear it ring, never smashing it. The current wiggles back at the same rhythm. But two things can change. The wiggle can be bigger or smaller. How hard the battery pushes back. And it can arrive a little early or a little late, a shift in timing. Those two numbers together are the impedance, the battery's answer at that one frequency. Here's the beautiful part. Why two numbers? Because a sine wave is really the shadow of a spinning arrow. Picture the voltage as a clock hand going round. Its shadow traces the wiggle. Now add the current as a second hand, spinning at the same speed, but trailing a little behind. That is the timing shift. Impedance asks, how do I stretch and turn the voltage arrow to land on the current arrow? And since both spin together, dividing them cancels the spinning entirely. What is left is a single, still arrow, a length and a tilt. Drop it onto a grid. Across is the ordinary resistor-like part. Up is the storing capacitor-like part. One frequency, one point. The spinning cancels, and what survives is a single dot. Now turn the dial. Sweep the rhythm from very fast, thousands of wiggles a second, down to painfully slow. At each frequency, drop the dot and watch the curve build itself. At high speed, the capacitors inside act like open wires. The current sails straight through, and all that is left is the bare resistance of the metal and electrolyte. That is the left foot of the curve, the starting resistance. Slow down, and now the current must cross the electrode surfaces. A resistor fighting a capacitor always traces a semicircle, and its width is the charge transfer resistance, how reluctantly the reaction happens. Slow down more, and the ions must crawl deep inside by diffusion. The curve rises into a long, slow tail, so remember the rule. Left is fast, right is slow. And here's the twist. That frequency dial is secretly a depth probe. Poke fast and only the surface jiggles. Poke slowly and the disturbance sinks deeper and deeper into the electrode each cycle. So the slower you ask the question, the deeper into the battery you are actually looking. Now the real surprise. You have seen two famous battery plots, the Nyquist and the Bode. They look completely different, but they are not two plots. They are two shadows of one single curve. Lift the impedance into 3 dimensions, flat position from the Nyquist, and frequency as depth, and turn it. The flat comma you knew lifts off the page into a ridge. Its shadow on one wall is exactly the Nyquist. Its shadow on the other is exactly the Bode. One curve, two shadows. So what does it actually tell us? The shape is a fingerprint. Bring back our mystery curve. The left foot is the wiring. The width of the arc is how sluggish the chemistry is. The tail is diffusion. Now cool the battery down and drain it low and watch. The arc swells dramatically. A cold, empty battery fights every reaction, and its charge transfer balloons. Warm it and fill it, and the arc shrinks back. That growing arc is how engineers spot a battery that is freezing, aging, or about to fail long before it dies. One gentle poke, one curve, the whole story of the battery without ever opening it. Next time, we will watch that fingerprint change as a battery ages, cycle by cycle.